Well, we'll continue our discussion of regression today. I guess if attendance in today's class is any indication, I forgot to send out the email about the discussion section. I guess I'll try to send out an email after class, or maybe we'll just have it and see what happens, but we're just kind of operating on the assumption nobody wants to come to discussion session at 3:30 the day before spring break starts, but I didn't email, so I guess maybe we'll end up having it. And also, if you didn't see already, homework 4 is posted. Sorry for not getting it done sooner. And the grace period for homework 3 will end tonight. If you need more time, it's fine. Just email me. Well, anyway, inference for regression today. That on Wednesday, we discussed how you can use regression to predict the value of a response variable y using a predictor variable x, but there are still questions that we may want to answer in the context of regression. Specifically, is an observed association that we see between x and y real? Do we see a stronger association than we would expect to see by chance? If we believe the association is real, how strong is this association? If we try to predict y based on x, then how confident are we in our predictions of y? And today I'll discuss how to answer each of those questions. So, first we'll discuss inferences about regression coefficients. Say we want to test the null hypothesis there's no association between x and y. In the overwhelming majority of cases, this is equivalent to testing the null hypothesis that the slope of the regression line is 0. Basically, the idea is that if x tells you absolutely nothing about y, then the best predictor of y based on x will just be y bar, the mean of y's. X will tell you absolutely nothing, and the slope of the regression line will be 0. If the slope is non-zero, that implies that as x changes, y changes. And one nice thing about this is you don't necessarily even have to assume the association's linear. If y increases exponentially as x increases, the association will be nonlinear, but if you try to fit a straight line to the data, it will still have positive slope. You'll still reject the null hypothesis that the slope's equal to 0. Really, the only way that you can get into trouble with this is if there's some sort of U-shaped association between x and y, that for a while y decreases as x increases, and then y starts to increase again. That's not common. In general, if people want to test the null hypothesis of no association between x and y, they'll just fit a regression, test the null hypothesis, the slope is equal to 0, and call that good enough. So this is one of the most handy uses for regression. In fact, I find in my day-to-day life, when I use regression the vast majority of the time, what I really want to test is this null hypothesis of no association between x and y. I'm much less interested in actually making predictions based on x. So, how do we test this null hypothesis? I'll show you here in a second. To explain how we can perform this type of hypothesis testing, I'll give a little background behind how this is done. For this class, for the most part, we'll just use R, so this isn't super important. Just help you understand the concepts behind it. The theory is that if our regression model is true and that y really is a linear function of x, then there's a population regression line that y is equal to b0 plus b1x plus an irreducible noise term. And we try to approximate this population regression line by a sample regression line that's estimated from the data. And this estimate of the sample regression coefficients will have a certain amount of error, and it's just like when we were trying to make inferences about the mean of a population, that if you take a sample of 100 people from the US population and take their height, that will not be exactly equal to the mean height. If we took all 300 million people in the US, there'll be a certain amount of sampling error in that estimate, and we can quantify that, the amount of sampling error, and try to draw inferences about the true population mean. With regression, you can do the same thing, that if we were to estimate a sample regression coefficients B0 hat and B1 hat, they'll be estimated with a certain amount of error, but we can figure out how these sample regression coefficients are distributed to make inferences about the population coefficients. So, it can be shown, I won't bore you with the details, and for the purposes of this class, this isn't something that you will need to remember, but you can show that the expected value of the regression slope B1 hat is equal to the population regression slope. In other words, the standard least squares regression estimate for the slope is an unbiased estimate of the population slope, and you can show that its standard error is equal to this expression here, where the standard deviation of y given x is this quantity down here. Now, like I say, don't need to worry about remembering this. I just put it in case you ever need the formula for some strange reason, also just to illustrate the point that it's possible to calculate the sampling distribution of the regression slope in this case. So, if we know the expected value and standard error of something, then we can apply the central limit theorem to show that if we take the estimated regression slope and divide it by its standard error, that will have a t-distribution with n minus 2 degrees of freedom, and we can use that expression to perform hypothesis tests about the regression slope. We can also calculate a 95% confidence interval for the regression coefficient by taking the regression slope plus or minus the appropriate quantile of the t-distribution times the standard error. I'm going to think that I probably should have put an alpha in there, oh well. So, going back to the stopping distances example, as you'll recall, we looked at the scatter plot and there was very compelling evidence that stopping distance increased as speed increased. We fit the regression line, it seemed to have a fairly strong positive slope. We might pose the question, is this association statistically significant, or more precisely, can we reject the null hypothesis that the slope of this regression line is equal to 0? So, as you'll recall from Wednesday, if we save the output of the lm command in R and then apply the function summary to the lm command, we get output that looks something like this. And the thing that we're interested in for today is, note that, as we saw before, the regression estimates are this minus 17.58 and 3.93. Also notice it gives a standard error for each estimate and a t-value, and it also calculates a p-value, the ID, which is the probability of observing a test statistic as extreme or more extreme is what we observed. In this case, the p-value is 1.49 times 10 to the minus 12. Very strong evidence against the null hypothesis that the regression slope is equal to 0. So in general, in R, if you ever want to test the null hypothesis, the slope's equal to 0, you can just use summary.lm and look at the p-values in this column right here, and that's really all there is to it. As an aside, you may notice down at the bottom there's also an F statistic that in this particular case that is exactly the same as the p-value for the T statistic. We'll discuss this F statistic more next Monday, but basically the difference between the T statistic and the F statistic, the T statistic here tests the null hypothesis that the slope for that particular variable is equal to 0. The F statistic tests the null hypothesis that all variables have a slope of 0. Now, in this case, we only have one variable in the model, so the T statistic and the F statistic are identical. On Monday, we'll discuss multiple regression, when you may have more than one predictor variable. In that case, the T statistics and the F statistics may be different from one another because you may have one particular variable whose slope isn't significantly different from 0, but you can definitely reject the null hypothesis that all the slopes are equal to 0. But as I said, more on that on Monday. And if you want confidence intervals for the regression coefficients in R, you can use this command confident. You give it an LM object, it will give you lower and upper 95% confidence bounds for both the slope and the intercept for a particular regression model. Most of the time, it'll be the coefficients for the slope that you're interested in. We see that the slope, that is the amount that the stopping distance increases for every 1 mile per hour increase in speed, ranges from about 3.1 feet to 4.8 feet. In general, if you say confident of an LM object, it'll give you a 95% confidence interval for the regression coefficients. If for some reason you want a confidence interval that's something other than a 99% confidence interval, you can do confident lm.object, a level equals 0.99 or level equals whatever value you want. And that will give you a 99% or some other value or a confidence interval. In practice, people almost always use 0.95. And let's say that we want to make inferences about the prediction of regression lines. In my experience, I don't use this nearly as often as inferences about the slope. I mean, as I said, the vast majority of the time when I use regression, I'm really interested in testing the null hypothesis that the slope is 0, or testing the null hypothesis of no association, than I am in making predictions. But sometimes we do want to use regression to make a prediction. And if we do this, we need to figure out how confident we are in these predictions. So, and this idea of confidence intervals for predictions based on regression, to be quite honest, confused me for years when I first learned about this. So I did my very best to explain this as clearly as possible, but if this is unclear, then let me know and I'll try to explain it in more detail. As you'll recall, on Wednesday, I gave the example where we tried to predict the stopping distance when the speed was 21 miles per hour. And when we make this type of predictions, there's actually two different things that we may be trying to predict. One possible thing we might want to predict is something like, given if we took all of the cars in the world, or at least the population of 1920s Model Ts, which is what this data set was based on, and took every single one of these cars, took them to 21 miles per hour and slammed on the brake, saw how long it took each of these cars to stop, and then took the mean of that over the entire population. That's one thing that we may be trying to approximate. The other thing we may be trying to approximate is, say we don't care about the population mean stopping distance for cars going at 21 miles an hour. We just have one single car driving down the street at 21 miles per hour, and we want to predict the stopping distance for that particular car. In that case, we're not trying to predict the value of the population mean. We're trying to predict the stopping distance for one individual in the population. Regardless of whether we're trying to predict the population mean or whether we're trying to make a prediction for one specific observation, the estimated values will be the same, but the confidence intervals will be different. Not surprisingly, the confidence intervals for the mean will be narrower than the confidence intervals for an individual. It's like, I don't know, I like to use the analogy of the forest and the trees for this. If you tried to use a regression model to predict the height of a tree, then whether you're trying to predict the mean height of the forest or the height of an individual tree, your prediction is going to be the same. You'll be much more confident in your prediction of the mean height in the forest than you will in the prediction of the height of an individual tree. So, the standard convention in regression that isn't always followed, somewhat confusingly. I'll try to follow it as best as I can in this class, though. An interval such that there's a 95% probability that it contains the mean stopping distance is called a confidence interval. An interval chosen such there's a 95% probability that it contains the stopping individual for a given car or a given tree is called a prediction interval. Now, a prediction interval is technically a confidence interval as well, so these two terms get used interchangeably sometimes, which causes a considerable amount of confusion. Like I said, for this class, I'm going to try my hardest. When I say confidence interval for a prediction, that always means confidence interval for the mean prediction, and when I say prediction interval, that means 95%, an interval that's chosen to have 95% probability of the height of an individual tree or an individual car, rather than the population mean. So, how do we calculate confidence intervals or prediction intervals? Say that we want to predict the value of y for a given x0, and regardless of whether we want to calculate a confidence interval or a prediction interval, the expected value is always the same, that y hat equals b0 hat plus b1 hat times x0. Not surprisingly, the best prediction of either the mean height of the forest or the height of an individual tree is just you plug in x0 to your regression line and see what you get. But the standard errors will be different in the two cases. And if you do a bunch of ugly math that I won't torture you with, the standard error for a confidence interval looks like this, and the standard error for a prediction interval looks like this. Certainly something you don't need to remember, and you will probably never use again. There's no way I would ever remember these formulas without looking them up. But the one thing that might be worth noting is note that they're exactly the same, except in the formula for the prediction interval, there's a +1 inside the square root, where there's no +1 inside the square root for the confidence interval. That implies the standard error for prediction interval is always larger than the standard error for a confidence interval. Makes intuitive sense. The expected predictive error in the height of a tree is always going to be greater than the expected predictive error of the mean height of the forest. So, to do this in R is your call. to make predictions based on a regression model in R, the command you use is called predict, and the command's called predict. To give the value of x for which you want to make predictions, you have to use this clunky syntax where you say new data equals data.frame speed equals 21, or in general x equals x0, where x is the predictor variable in your model. Note that we added new parameters here where we say interval equals confidence or interval equals prediction. If we don't specify this interval parameter, it gives the predicted value of y and leaves it at that. It doesn't give you any type of confidence interval. But if you say interval equals confidence, then it gives you a 95% confidence interval for the mean predicted value of y. If you say interval equals prediction, that gives you a 95% confidence interval for the predicted value of an individual observation. This tells us that based on this regression model, if we took the entire population of 1920s Model Ts, drove them to 21 miles per hour, hit the brakes on every single one, and then took the mean value of the stopping distance for across all the cars in the population, this interval that we chose here from 58.6 to about 71.4 shows as a 95% probability of containing the true value of the population mean. If we only looked at one car rather than the mean across all cars, the 95% prediction interval goes from about 33.4 to 96.6, which, not surprisingly, is larger than it is for the population mean. And in general, if you say predict lm.object new date equals whatever, and then interval equals confidence, that'll give you a 95% confidence intervals for the predicted mean values of new data using this regression object. If you want prediction intervals, change interval equals confidence to interval equals prediction. If you want a confidence level other than 95%, you can say level equals 0.99 or whatever. Again, that's not commonly used. And if you don't specify new data, it will calculate this for all the x's that were used to fit the original model. Another statistic that's commonly reported for regression models is a statistic called R squared, which basically, the formula for R squared is this. The intuition is it's supposed to be a measure of how well the regression model fits the data. You'll notice the numerator of this fraction here is just the true values of y's minus the predicted values of y's. The sum of the squared error is precisely what the regression coefficients are trying to minimize. The denominator is yi minus y bar. Recall that if there's no association whatsoever between x and y, then the optimal regression slope will be 0, and the optimal predictor of y given x will just be y bar, because knowing x doesn't tell us anything about y, so the best prediction of y is just the mean value of y, not surprisingly. So basically, the idea is that the smaller this fraction is, the better prediction that your model is. That if the perfect scenario, if this fraction is 0, then that means that your regression model is predicting y's with no error whatsoever, implies you get perfect predictive accuracy. On the other side, if this ratio is 1, that implies that the prediction based on the regression line is exactly the same as the best prediction if you didn't know x in the first place, where you just estimated everything to be y bar. In that case, you have no predictive accuracy whatsoever. So R squared just tells you, it gets a measure of the predictive accuracy of the model. 1 implies perfect accuracy, 0 implies no accuracy at all. And if you play with the math for a minute, in the case of simple linear regression where you only have one x variable, then R squared turns out to be equal to the correlation coefficient R squared, not surprisingly, hence the name R squared. As you'll recall, the correlation coefficient is always between 1 and minus 1, hence R squared is always between 0 and 1. And the way you can interpret R squared is that R squared measures the amount of variability in Y that can be explained by variability in X under the regression model. In other words, like if R squared equals 0.75, then that means that 75% of the variability in Y can be explained by variability in X. And R squared is automatically calculated if you use the summary.lm command in R. If we do summary of cars again, you'll notice down here at the bottom, C multiple R squared equals 0.6511 in this case. That tells us that about 65% of the variation in stopping distance can be explained by variation in the speed of the car when you stop. Adjusted R squared, just because someone inevitably asks about that. Short answer, for the purpose of this class, you can just ignore it and not use it for anything, and I'm perfectly happy with that. Slightly longer answer, if you're curious, is that you can show mathematically that R squared will never decrease as you add predictor variables to your model. On Monday, I'll discuss multiple regression, where you try to predict Y based on several X variables. And in that case, if you add more and more X variables to your model, R squared will always get better, even if there's no real association between X's and Y's. The adjusted R squared tries to take into account the fact that R squared increases as the number of variables increases. And so if you start adding too many irrelevant things, then adjusted R squared will start to get worse, at least in theory. In my experience, the problems with adjusted R squared is, number one, in practice, it doesn't seem to be very much different from R squared in pretty much every example that I've tried. Number two, nobody uses it. So, yeah, like I say, you can just ignore it and it's fine for this class. I don't think I've ever seen a single paper or anything in my entire life that reports adjusted R squared. And some comments on R squared. Keep in mind that R squared only measures the variance in Y explained by variance in X under the assumption that the model is true. So, if the regression model is true and that Y really is equal to B0 plus B1 times X plus noise, then saying that the percentage of variation in X that can be explained by variation in Y is 0.7 if R is 70% if R squared equals 0.7 is the true statement. However, say the association between X and Y is exponential, and it's a perfectly exponential relationship. Say that Y is literally equal to 2 to the X or something like that. If, in theory, 100% of the variation in Y would be explained by variation in X, because if we knew that association, you could predict Y with perfect accuracy given X. But if you fit a simple linear regression model to it and tried to fit a linear model rather than an exponential model, then then you'll still get an r squared less than 1, even though the true value of r squared is 1 in a certain sense in that case. And the value of r squared that's considered to be high is extremely context dependent. I sometimes get collaborators that say, well, the r squared is only 0.3 or whatever. That's a really weak association. Well, it depends. I mean, to give one extreme example, if you're converting between Celsius and Fahrenheit, any sort of r squared less than 1 is totally unacceptable, because you should be able to do that with perfect accuracy. Or if you're just calibrating one instrument against another instrument, you probably won't get an r squared of exactly 1, but if you're not getting an r squared of extremely close to 1, then probably one of your instruments is badly out of whack and needs to be repaired. Now, on the other hand, if your objective is to predict which direction the stock market will go over the course of the next year or the next 3 months, if you can get an r squared of like 0.05 in that case, then you can either publish your model and win a Nobel Prize, or you can not publish your model and get millions of dollars on Wall Street. If you get an r squared of 0.05 in that context, you're going to be incredibly happy just because the stock market is so incredibly random and difficult to predict. So it's a bad idea to just say only an r squared above a cutoff of whatever actually matters, because a good r squared depends very heavily on what you're trying to do with it. As a quick aside, you may want to calculate confidence intervals for r squared. There's a couple times I've been asked to do this in real life. There's no good way to estimate the sampling distance distribution of r squared. So, and there's a typo here, that if you want to compute the confidence intervals for r squared, you need to use bootstrapping. And this isn't something that I anticipate asking you to do in this class, but I'll give you the code here just in case you ever need to calculate confidence intervals for r squared in the future. If you define a function r squared dot boot, which as usual takes two parameters, x and I, do x dot, again, we assume x, just like we did with the correlation, we assume x is a matrix with two columns, where one column is the predictor variable, the second column is the response variable. So we do x dot star equals x of I, comma. In other words, we sample from the rows of x with replacement, and then we fit a regression model to predict the second column, i.e. the response variable, based on the first column, which is the predictor variable. And then to extract r squared, we take the summary of that LM object and say $r dot squared. That's kind of an advanced R trick that's really beyond the scope of this class that I don't ever plan to ask you to do. This is just to illustrate if you ever need to calculate confidence intervals for r squared, this is how you can do it. So, in general, if you say summary lm.object $r dot squared, that will give you the value of r squared for that regression object. You generally only need to do that if you're trying to do something fancy like we're doing here. And most of the time you can just use the summary command and just copy down whatever it is. And as you'll recall before, if we say x1, comma, that gives the first row of x. So if we say xi, comma, that resamples from the rows of x with replacement. So if we want to calculate 95% confidence interval for r squared for the CARS regression model, we feed the input data, as I said, it has to be a matrix with two columns, where the first column is the predictor variable, the second column is the response variable. We can use the cbind function to create a matrix with these two columns. Cbind tells our to create a matrix where the first column is equal to speed, the second column is equal to distance. Then we give it this r².boot function, 1,000 bootstrap iterations, and then we can use boot.ci to get confidence intervals. Note here, once again, we get the warning that some BCA intervals may be unstable. So in this case, I would probably report the percentile intervals that go from about 0.49 to about 0.78. In this case, note there actually is a noticeable difference between BCA and percentile, which is why I would be nervous reporting BCA in this case. If you really wanted the best confidence interval possible, you could try like 10,000 or 100,000 bootstrap iterations in order to try to get better BCA intervals, but yeah, that's much beyond what I would ask you to do in this class. And one other quick thing worth mentioning is regression through the origin. In my personal opinion, I pretty much never use this, and I'll explain in a minute why I think it's a bad idea to use this, but occasionally people will want this, so I'll explain how it's done in case you ever need it. In many situations, you may have a reason to believe that the value of y will be 0 if x is 0. For example, in the cars example that I've been using for the last couple lectures, if a car is moving at 0 miles per hour, it seems reasonable to think that the stopping distance will be exactly 0 if you slam on the brakes 0 miles per hour. Okay, fair enough. And this also avoids the issue that for low values of x under the car's regression model, we get a predicted negative stopping distance, which is somewhat problematic. So we may say, given that we don't ever want to predict a negative stopping distance, and given that it seems reasonable to think that the stopping distance will be 0 if the speed of the car is 0, let's force the y-intercept b0 to be 0 in this regression model. So to do regression through the origin in R, the syntax is the following. Rather than doing the syntax before we said lm distance twiddle speed, the syntax we use is distance twiddle speed minus 1. The minus 1 tells R that we should not include an intercept in this model. So you'll notice now in this case we get a regression slope of about 2.9, and we don't have an intercept in this model like we did earlier. You'll also notice suddenly our r² is much higher and our p-value is much smaller, and you might be tempted to think, whoa, the prediction got much better when we got rid of the intercept. Actually, that's not the case, as I'll explain here in a minute. So, and in fact, that's the reason why I don't like using regression through the origin, is it can give potentially misleading results like that. In general, in R, if you say y twiddle x minus 1, that tells R to fit a linear regression model with no intercept in the model. So why do I say not to use this particular, not to use regression through the origin, or why I don't like to use it at least? If we do ordinary linear regression where we have the intercept term, then the null hypothesis of no association between x and y is equivalent to testing the null hypothesis of no association between x and y is equivalent to the null hypothesis, the best possible prediction of y for any given value of x is just y bar. That x gives you no information about y. If you want to predict y, the best possible prediction is just the mean value of the y's. Okay, fair enough. But if you force regression through the origin, then you're forcing a much more stringent null hypothesis. That is, that you're testing the null hypothesis that y equals 0 against the alternative hypothesis that y equals b1 times x. And in the vast majority of cases, we know darn well that y is not equal to 0 for all y's. So so clearly there's always overwhelming evidence, or virtually always overwhelming evidence, to reject the null hypothesis that y is equal to 0. So pretty much any time you fit a regression model through the origin, you're going to get an R-squared that's absurdly high, p-values that are absurdly tiny. These numbers are totally meaningless. You've convincingly shown that your data is not equal to 0 for every value of y. Wow, never could have done that without a formal hypothesis test. So that's why I don't recommend ever using regression through the origin, even in situations where it seems reasonable not to include an intercept in the model, just because when I use regression, the vast majority of the time, the null hypothesis that I really care about is the null hypothesis that the slope is 0. There's no good way to test that hypothesis without including an intercept in the model. So that's why I always include the intercept in the model, even in cases like the cars example where you get nonsensical things like predicted negative stopping distances. It's the price you pay to be able to make reasonable inferences about the slope. And as you'll recall, when we performed t-tests and other tests in the past, I used to scream about the fact that you can get into trouble if the assumptions of the t-test aren't satisfied, that the data is a random sample from the population, the observations are independent, and that the data is approximately normally distributed for a small sample size. If these assumptions are violated, then our inferences can be invalid. And likewise, to make inferences on regression model, there's a bunch of assumptions that we'll be discussing I guess it'll be after spring break, but over the next few lectures. And regression is even more problematic than the t-test in this regard, in that for the t-test, the assumption that it's a random sample from the population, the observations are independent, the vast majority of the time, those assumptions are going to be true, and it's not that hard to find data that just come up with an experimental design such that those assumptions are true. Regression, on the other hand, to do it perfectly requires much more stringent assumptions, and I don't think I've ever seen a real data set in my entire life where those assumptions are really satisfied perfectly. And so that means we either have to throw up our arms and say regression is useless, or you have to understand if these assumptions are violated, what happens and how does that affect our inferences. And that is a lecture or several whole lectures in and of itself. I think it'll actually be Erica that gives those particular lectures because I'm going to be out of town most of the week after spring break. But this is just a preview of coming attractions that you have to make these assumptions in regression models. They're frequently violated, and we'll be devoting quite a bit of time to figuring out if your regression assumptions are satisfied and how it affects your conclusions if they're not satisfied. So, things to remember for today is you can calculate a sampling distribution for regression coefficients and predictions, and you can make inferences about these values. It's possible to do regression through the origin, although in practice I think it's a bad idea more often than not. And new R commands for today, confident will give you confidence intervals, and predict with interval equals confidence or interval equals prediction will give you confidence intervals and prediction intervals for predicted values of y in a regression model. Any questions for anything we discussed today? Okay. Enjoy your spring break, and if you have any try to design it so that you don't have to do too much homework over spring break if you don't want to, but I should be on email over all of spring break if you are doing homework and have questions. I say, like, the punishment should fit the crime in my book. If I give you work over spring break, I need to be available to answer questions.